Hi everyone. So in this video, we're going to go ahead and discuss something called the limiting reagent, the excess reagent, and then the theoretical yield and percent yield. So let's go ahead and get started. Okay, so first thing I want to do is kind of clear up the difference between reagents and reactants. Reactants are the starting materials of a chemical reaction, so the stuff that's on the left-hand side when we write out that reaction. A reagent is a substance added to a chemical reaction in order to produce the product. So for our purposes, they're pretty much the same thing. So you might see limiting reagent or limiting reactant. Just know it's the same thing. It's just slightly different definitions of the materials that we're putting into a reaction. Okay, so now I want to go ahead and define this idea of the limiting reagent and the excess reagent. The limiting reagent is the reactant that limits the amount of product that we can produce. So at the end of the reaction, it is completely used up. We don't have any more, which is why the reaction stops. The excess reagent is the reactant that is left over after the reaction is run as far as it can go, but is run out of something else, so we have a little bit extra left over of the excess reagent. The limiting reagent determines the theoretical yield versus the excess reagent does not determine the theoretical yield or how much we can make. Now, if we're trying to develop the reactions so they're most efficient, we usually have the limiting reagent set as either the rarer or more expensive reactant because we don't want to be wasteful. In contrast, the excess reagent tends to be the less expensive thing or the more common reactant. So if we think about combustion reactions, we have the hydrocarbon plus oxygen. Well, oxygen is really plentiful. It's all around us. So that tends to be the excess reagent, and the limiting reagent tends to be the hydrocarbon in that example. So let's go through a real life example. You are having a barbecue and stop by the store to buy some supplies. And you find out that hot dogs are sold in packs of 10, but hot dog buns are sold in packs of 8. Which is kind of the eternal problem. So if you buy one pack of each, which one is your limiting reagent? Well, we know that one serving is one hot dog plus one bun. So because we only have 8 buns, that is going to be our limiting reagent. The thing we're going to have left over is our excess reagent, which is the hot dogs. Okay, so for a slightly different take on that, you're now having a large barbecue. So you stop by the store to buy some supplies. This time, you end up buying 5 packs of hot dogs and 7 packs of hot dog buns. Okay, so we want to figure out which our limiting reagent is. So the way we do this, we first need to find out how many we have of each individual item. So we have 50 hot dogs if we have 5 packs of 10. And we have 56 buns if we have 7 packs of 8 buns. So if we look at this, the smaller number, the one we're going to run out of first, is going to be our hot dogs. And in this case, our excess reagent is the hot dog buns. So even though we have that same idea of one hot dog plus one bun equals one serving, it changes based upon the number of the different starting materials we have. There are a few steps to finding limiting reagents when doing stoichiometry. First thing is we want to start with a balanced chemical equation. That's always the first step for stoichiometry problems. Then, using stoichiometry, we want to calculate the amount of product in grams formed by each reactant. Okay, and then once we've done that, we find out that the reactant which produces less product is the limiting reagent, and that amount that is being produced by the limiting reagent is the theoretical yield. And then the reactants, usually it's one, but sometimes there's multiple of them, that produce more product are the excess reagents, and there's going to be some left over of those products. Let's go ahead and try out an example of this. Okay, so let's go ahead and try out an example problem. Now, the big thing to remember with limiting reagent is you're basically doing 2 stoichiometry problems to solve one question. But otherwise, you've done most of this before, so let's go ahead and get started. 79.1 grams of zinc reacts with 0.900 liters of 2.5 molar hydrochloric acid in a single displacement reaction. Identify the limiting and excess reagents. And then we want to figure out how many grams of hydrogen will be formed. Okay, so we're already given our balanced chemical equation. Remember, that is always step 1 when we're doing stoichiometry problems, so that is good. The next thing is to take the given and convert it into moles. And in this case, we have 2 different givens. The first one is 79.1 grams of zinc, so that's going to be our first stoichiometry problem. The second thing we're given is 0.900 liters of 2.5 molar HCl. That is our second given for our second problem. So let's go ahead and do the first one. So we have 79.1 grams of zinc, and I want to get that into moles of zinc. So I'm going to use the molar mass of zinc. If I look on the periodic table, it is 65.38 grams of zinc per 1 mole. The next step is I want to go ahead and use my mole ratio for my balanced chemical equation to go from moles of zinc to moles of hydrochloric acid, which in this case is a 1-to-1 ratio. Make sure you line up your values so that they cancel on the diagonal. And then the final thing, I want to find the grams of hydrogen. So moles goes on the diagonal so they cancel out. And every 1 mole of hydrogen weighs 2.02 grams. Okay, so that is my first table all set up. So let's go ahead, we're going to multiply across the top, divide by the bottom. So 79.1 times 2.02, and then divide by 65.38. So that gives an answer. Well, did that a little wrong, so let's go ahead and try it again. 79.1 times 2.02 divided by 65.38. Okay, that looks a little better. So that gives me 2.44 grams of hydrogen. Again, I want to always match my number of sig figs to my given, which in this case is 3. So that's my first stoichiometry problem. I'm going to now do my second one, which is my hydrochloric acid. So again, I'm going to take my given. Remember, it's always going to be the volume, so the 0.99 or 0.900 liters of HCl. The molarity is always going to be my conversion factor to help me get to moles. So that's going to be 2.5 moles of HCl per 1 liter of hydrochloric acid. So that is my step 2 of my stoichiometry problem. Step 3 is my mole ratio. So I'm going to have moles of HCl going to moles of hydrogen gas. So that is 1-to-1 for my balanced chemical equation. And then the same step, I want to use the molar mass again of hydrogen to find the number of grams that I can produce. Okay, so numbers up on top, I multiply. Numbers on the bottom, I divide. So 0.9 times 2.5 times 2.02. Oh, and one little quick mistake I see. For my balanced chemical equation, make sure you're checking your coefficients. It's a 2 this time. So then I'm going to divide my answer by 2. Okay, so that gives me an answer of 2.27 grams of hydrogen. Okay, so if I go ahead and look at this problem, my theoretical yield is going to be the smaller of the two numbers, which 2.27 is smaller. So that's going to be my theoretical yield. My limiting reagent, therefore, is the thing that I start with for that problem, so the HCl. And the other one is going to be my excess reagent, so that's going to be my zinc in this case. Okay, so when we have reactions, there's different ways we can describe the amount of product we get. The first one is the theoretical yield. This is how much product you will get if the reaction goes perfectly. And this equals the amount of product predicted by the limiting reagent. However, if we think about it, nothing in life really ever goes perfectly, so we're rarely going to actually get our theoretical yield. So what we actually get is something called the actual yield, which is how much stuff we get in the real world. And this is your experimental value. Finally, in order to compare these two numbers, we have something called the percent yield, which describes how well the reaction went. And sometimes reactions just are naturally bad. They don't give us a whole lot of product. Sometimes it's a matter that humans, we make mistakes when doing the lab, so that causes us to lose some of our product. But percent yield can be used to describe how well the reaction went overall. The equation for percent yield is the actual yield divided by the theoretical yield times 100%. And just kind of a general rule of thumb, you have a pretty good percent yield if you have 90+%. Acceptable yield is somewhere around 80, and then poor yield would be something around 60 or so percent. Below that, it would be a not good or a bad yield. But some reactions, like I said, just aren't very efficient and we don't get a lot of product. And that's okay. Okay, so let's go ahead and try some examples of percent yield. Okay, so let's go ahead and try an example. If you collect 1.75 grams of hydrogen gas, what is the percent yield from example 1? So remember, to find the percent yield, it is the actual yield over the theoretical yield. Well, the actual yield is given to us as 1.75 grams. The theoretical yield, that's what I calculated in that previous problem, so that was a 2.27. Remember, my limiting reagent tells me which one is the theoretical yield. And I'm going to multiply that by 100. So 1.75 divided by 2.27, and then times 100. So if I go ahead and put that in my calculator, I get 77.1%. So not great, but not too bad. And since in this case I'm collecting a gas, it's reasonable I could lose some. So that is my percent yield for this problem. Okay, so now I have a problem for you to try on your own. If 23 grams of iron 3 chloride, so make sure you have that 3 there, chloride, reacts with 41 grams of sodium phosphate in a double displacement reaction, how many grams of sodium chloride can be formed? So that part there is asking for the theoretical yield. So in this case, we can do 2 different stoichiometry problems. The first one, you start with the 23 grams of iron 3 chloride. The second one, you start with 41 grams of sodium phosphate. And in both cases, you're going to grams of sodium chloride. The next step, once you have that, is to determine the limiting reagent and the excess reagent. And then finally, you're going to find the percent yield if you have 16.1 grams of sodium chloride that is collected from the reaction. Now, to give you a jump start, here is the balanced chemical equation. What I would like you to do at this point in time is go ahead, pause the video, try it on your own, and then once you think you have the answer, come back and check your work. Okay, so as we work through this problem, we start with 23 grams of iron chloride, and we want to get to grams of sodium chloride. So we can go through that process. We get 24.9, or round for sig figs, 25 grams of sodium chloride. When we go ahead and calculate 41 grams of sodium phosphate, 2 grams of sodium chloride, we end up with a value of 44 grams of sodium chloride. So now when we compare these two, we see the smaller number is, of course, that 25 grams of sodium chloride. So that is our theoretical yield. So therefore, the iron chloride is our limiting reagent, and the sodium phosphate is our excess reagent. So the final thing we need to do now is go ahead and find the percent yield. So we're going to take the actual yield, which is 16.1 grams. Remember, that's given to us. And we're going to divide it by the theoretical yield, which is 25, and then multiply that by 100. So if we go ahead and put that into our calculator, 16.1 divided by 25 times 100 gives us a value of 64.4, or to round a little bit, 64% for our percent yield. So I hope that helps. If you have any questions, please go ahead and let me know. Otherwise, have a great day, everyone. Bye.